Greetings and welcome to the Servigistics webcast. My name is Bradley Roten and I'll be your host for today. Today we're discussing safety stock and how new technologies impact that safety stock and therefore material planning. We're excited to have a global audience and we appreciate you taking the time to join us for this webcast. We're looking forward to the discussion. And by way of housekeeping, this is a webcast series, which we do promote through our Servigistics LinkedIn page. Feel free to follow that page for recurring updates on a webcast, but also articles and other Servigistics news. At the end of this webcast, we will host a Q&A with the time we have remaining. The recording will be made available. We'll follow up via email to make sure you have access to that recording so you can share it with colleagues or replay as needed. And for any follow-up, feel free to email me at broten@ptc.com. With that, I'm excited to introduce our presenter, Ed Wadarsky. He's a popular Servigistics webcast presenter and also a popular LiveWorx presenter. Many of you may know him from previous webcasts, but he has over 4 decades of expertise with service supply chains and a very strategic way of thinking and simplifying complex topics on top of designing the first commercial service parts management solution. So we're excited to have him join us today. And Ed, I'm going to pass over the controls to you. And thank you for joining and sharing your time with us. We're looking forward to your comments. So take it away.
Thanks, Bradley. Good morning. So, as described, I'm going to talk about 5 emerging technologies and their implications for service parts planning and the role it will play in next generation planning environments. People have asked me why I chose to talk about this in terms of safety stock. And I think you can argue that stocking levels are the critical output of a material planning system, because without them, the demand plan is not actionable. And a supply plan has no context. So they really are the value fulcrum to a material planning system. And we accept that the fundamental role of safety stock is to cover variability of demand over lead time, and then we take a look at the hype in the marketplace around especially 2 technologies, predictive maintenance and 3D printing. If you believe all the hype, you could conclude that the need for carrying inventory in itself may soon be over. The logic behind that is that predictive maintenance eliminates the demand variability, and 3D printing erases the lead time. So the 2 things that safety stock and stocking policies compensate for evaporate. But is this all really true? And what I'm here to advocate is that the report of my death was an exaggeration, which is the correct verbiage of that quote from, of course, Mark Twain. And so I'm going to describe how I think we coexist very successfully with 3D printing and predictive maintenance while needing to adapt to them, of course, and how we thrive with the introduction of the other technologies that we're going to talk about today. So I'm going to start with predictive maintenance. And as many of you, I'm sure, are aware, what we're talking about here is the application of sensor technology to observe how assets are performing in the field. And by establishing tolerances around that performance or around metrics that gauge the health of the asset, we can look at likely part failure predictions, which is extremely valuable, because we can look at doing the maintenance during scheduled downtime of the equipment rather than having an outage that is much more complicated and costly to resolve. And for those of us that are dealing with high cost of outage assets, I know we have some people from airlines here, that certainly fits the bill, as do refineries, production lines, high volume servers, all of those things where the cost of outage is extremely costly to the owner or operator of that asset. So by monitoring the asset performance we can avoid costly loss of service. So there's certainly great value in predictive maintenance, and I don't intend to diminish that. I just intend to talk about how we coexist with it. And the financial benefit, of course, is that by being able to schedule the maintenance when it's appropriate for us to do it and avoid downtime of the asset, we reduce service costs and improve the overall asset availability. So it's a win-win for the person utilizing the asset and the person maintaining the asset. So what does it mean for material maintenance? Well, the impact is really on service delivery, which will be dramatically improved for all the reasons we talked about. For even less critical assets, just being able to understand that a laptop or something else is going to crash allows us to source service providers, launch technicians, pre-position parts. All of those things will improve the ability to deliver service. But what we need to understand is that these failure predictions are themselves probabilistic. So when we're looking at a temperature gauge or a pressure monitor, we're guessing that if it's out of tolerance, that the part's going to fail, which may or may not be true. So while we hope the accuracy is high because it benefits everyone, there are still going to be needs for us to forecast around those parts, even if they're sensor-based, because they are not going to catch every part failure. Right now, anyway, the ability to apply predictive maintenance still applies to a fairly small minority of parts, I'm sorry. And so the vast majority of the balance of those parts still need to be forecasted and planned through traditional methods. The complications are the ability to apply sensors and correlate that to part failure. Some applications are just environmentally difficult, which is one of the challenges for an airline, where you can't just go sticking metal things anywhere that you would like to use as a source for capturing data. The good news, though, is that the applicability of predictive maintenance is highly concentrated on what turn out to be critical parts. And as they're critical parts, they have a greater impact on the asset availability. And so that's good news that the focus is on the parts that are going to best improve the asset sustainment. So what's it mean for us as parts planners and forecasters? So it's not going to impact how material planning is performed. What it will impact is forecasting. What we need to do is to figure out where performance is degrading, recognize that not all part failures are captured by the sensor, and how do we pick up the rest. The other challenge is that these predictions of failure almost always happen way too far inside lead time to impact a supply plan from a sourcing standpoint. We might be able to redeploy inventory, but we can't go and source it. So what we need to do is maybe forecast the forecasted predictive maintenance failures so that we're able to establish a long-term supply plan. And then we have to figure out, how do we properly net the failures that were indicated by predictive maintenance activities versus the ones that weren't, so that we're very careful to avoid double counting failures, which would, of course, overstate the inventory. So we look forward to the benefits of predictive maintenance, and we're rapidly adapting our application to understand that stream of data and how to react to it. If you're familiar with PTC, you know we have a very strong foothold in the Internet of Things and how that impacts production and service. And we've launched a connected service parts management application to take advantage of that platform. And so what we're really trying to do here is not predictive maintenance. Predictive maintenance is the prediction of a failure of a specific part in a specific piece of equipment. What we're trying to do is leverage what data we can capture from the entire population of assets and use that to influence the forecast and other sources of data related to planning. So we advocate for our customers that demand history alone is not a particularly good forecasting methodology, and advocate the use of forward-looking forecast methods. And those forward-looking forecast methods typically involve some sort of metrics around the installed base in terms of how many units are being serviced, or maybe even the activity profiles of those assets, such as the flight hours and cycles of a fleet of aircraft. But the challenge here is that those streams of data are themselves forecasts. Airlines have a little greater handle on their flight schedules, but for most other verticals, the number of assets in the field or how much they're being used are projections created by marketing or other organizations. And so those streams of data can actually introduce a different type of uncertainty into the forecast model. And the whole point of the planning engine is to take uncertainty out of the model. So the vision we have for connected assets is to replace that stream of projected inputs, that proxy data, with actuals. And what I mean by those actuals are, if we're able to interact directly with the equipment, we can figure out exactly how many assets are in the field. We can figure out geographically where they're deployed, which for people like John Deere, where equipment moves around over its 30 or 40 or 50-year life cycle, that's extremely valuable information for determining how to position inventory and how to correlate demand with dealers. And we can also begin to look at establishing forecasts around assets or groups of assets, which gives us that projection of what the future activity of those assets might be, which is fundamental to a causal or installed-based forecast. So the benefit of this capture of data is increased forecast accuracy because we're replacing proxy data with real data. And we're able to develop matrices around failure rates. And what I mean by this is today, most people distill a failure rate for a part down to a single value. It fails once for every 10,000 operational hours. Well, the problem is that part may be applied to 10 different products in 100 different configurations over multi-decade lifespans with different environmental considerations and different applications of the asset itself, which may have great influence over the likelihood of failure. But if we're now capturing activity profiles on individual pieces of equipment for which we can identify where it is, how old it is, which model it is, and potentially infer from that environmental considerations or the way the equipment's being applied. For example, is it a piece of heavy equipment that's being used in an extremely rocky terrain or sandy terrain or wet terrain? Those considerations can now all be accounted for. And instead of having one failure rate, we can have a failure rate for this part related to this product in its initial launch versus its end of life applied in this way in this environment, which will further refine the ability to generate forecasts. It'll also further refine distribution strategies, dealer relationships, all of the things related to pre-positioning of inventory. And because we're now capturing data with lots of different attributes around it related to failures, it's an interesting feedback loop to engineering and reliability. Big data, machine learning, very, very popular buzzwords and things that bristle with potential. So there are a few different definitions of machine learning, but if we take a fairly basic one, that it's an application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. Well, what does all that mean? Well, typically when we write code, we define a set of inputs. We define some algorithms or processing logic to manipulate those inputs to create desired outputs. Now, what happens if we have a whole bunch of ill-defined inputs, an ill-defined set of processing logic, but a defined set of outputs? And that's exactly what the path that Servigistics is taking in how we react to these technologies. So if you look at the evolution of big data for parts planning, the traditional role had been to monitor the supply chain. And what that meant was we have defined data structures around locations and lead times and parts and part attributes. And we've developed data around that where we have reports, which are sort of snapshots of where we are at a point in time, and dashboards that maybe can allow us to interactively explore that performance into lower levels of granularity for root cause analysis and issue identification. And we generate a lot of part-centric planning data, which is all very, very important. But what we now have, especially with the advent of IoT and connected assets, is the ability to monitor the assets themselves, which exponentially expands the amount of data that's being captured. So we now look at what are we doing in the planning engine to leverage that? Well, we've got a connected SPM model. We've developed a performance and intelligence model that allows us to now look at time-phased planning data in greater volumes than we were ever able to meaningfully process before. And what that allows us to do is apply these machine learning tools to make sense out of those huge volumes of data and figure out how we're able to create a better planning model with better results at lower costs. We've always had a form of machine learning in a way, because if you look at how multi-echelon optimization operates, it has a goal based on a least cost objective function to meet the service goals at least cost. But how it gets there is largely figured out as it's executing. So we establish a series of service goals, which can be represented by fill rate targets at a warehouse, performance-based logistics or service level agreements, contracts, all of those things simultaneously. And then the algorithm considers every trade-off between whether it stocks a part at a location in this period of time, and it explores all of the alternative scenarios until it comes up with the one that meets the objective function and achieves the service goals at lowest cost. So if we look at that as our toehold into the ability to do machine learning based on extensive data sets, it takes planning on a path to autonomous planning. And while I don't think we'll maybe we will, but maybe not in my lifetime, see to the point where we don't need human intervention. But the point is, we've always had a philosophy of management by exception to maximize the productivity and the value created by individual planners. And the extension of that is, instead of just automating the routine, let's figure out why issues are arising in the first place and try to correct them before they occur. So we're applying machine learning to make sense of big planning data. And we're observing the supply chain and its performance and observing the assets within that supply chain. And by looking at this data over time, we can observe the impacts of planner actions. If they're presented with this challenge, they took this action, did we get the desired result? And by filtering out those actions, we can learn from the big data resources which actions under which circumstances are leading to the desired result. Being able to automate that, then this intelligence can refine the planning model, meaning the parameters within it, whether they be related to forecasting parameters or the fine-tuning capabilities within the multi-echelon optimization or stocking policies or redistribution priorities. All of those things can now be intelligently refined and further improve the value of the data the plan's generating, and in the long run begin to significantly reduce the number of issues that arise, creating challenges for the supply chain and actions on the part of the planner. So 3D printing. 3D printing has amazing potential. I was just reading an article this morning that there's a nuclear reactor that's being brought on board in 2023 where its entire core was generated by 3D printed components. And, you know, if you think about where we were just a few years ago, we were talking about a fairly limited set of things that could be developed via 3D printing, primarily based on plastics and simple parts. Well, that's rapidly changing. So what's the impact of 3D printing on material planning? So it really does promise the capability to create inventory on demand, which would diminish the role of demand planning, because if you as soon as you receive a demand, you can create the inventory. Certainly, there's not a lot of need for long-term forecasting for those assets, and it shifts the focus primarily to the raw materials and the resources that are needed to drive the 3D printing process. It may be able to rationalize supply chains with a fewer set of suppliers and a simplified supply chain. Production can be done in smaller lots, allowing for a lot more flexibility in producing these parts, further collapsing the lead time and increasing the value of the 3D printing process. And because we can do things in small lots, it has implications for obsolescence and excess. So instead of being forced to buy in economic order quantities, we're producing in much smaller quantities that are intended to be consumed almost in real time, so that the concept of excess becomes irrelevant and parts aren't obsolete because we didn't build them until we needed them. It also gives the opportunity to produce some parts locally, where even the transit component of lead time gets to be collapsed to some extent, reducing the aggregate overall lead time of responding to a demand pulse in the network. And of course, given our earlier definition of safety stock, the collapsed lead time is of course going to reduce the amount of inventory that we need. And what we see is an expanding scope of materials. So what started out largely as plastics and polymers, and now it's extended to resins and glass and ceramics and metal alloys and pure metals. So the materials that comprise parts generated by 3D printers has exploded, and exploded in ways that create opportunities that were not foreseen just a few years ago. But there are some constraints. There are some things that will always require some sort of assembly process or combination of multiple materials, some of which may not be candidates for 3D printing. Things like electronics are good examples of that. We also have to understand the role of partnering here. Service providers, unless they're an extension of the OEM itself, which is rarer and rarer these days, they do not own the intellectual property and the copyrights of these parts. You know, the aviation world's been dealing with this with PMA parts for decades, where non-OEM suppliers can get certified that they can produce the part that meets all of the criteria for that part being airworthy. Well, imagine that for every part being applied to 3D printing. Service providers are going to have to figure out a way to get access to the intellectual property and the copyright, and that means there's going to have to be some way to compensate the OEM for them forfeiting part sales. So that's going to create a fair amount of complexity, which is going to have implications for the rate of adoption for 3D printing. There are also a number of case studies suggesting that while for simple things, 3D printing is relatively easy, but for more complex parts, there are adoption and training issues. There are even environmental issues, because the fine particulates that are being used in this process are getting into the air and potentially creating hazards for the workspace. So the ability to deploy 3D printing closer to to the customer, closer to the demand signal, is going to be inhibited by the ability to deal with these issues. But there are certainly some very encouraging case studies. One article I read about a particular part was GE aircraft engines built a fuel intake that was 18 separate components, and they did it all via 3D printing, and the resulting assembly was more reliable, the seals were tighter, improving its performance, and it had a lower mean time between replacements. So the applicability of this is clearly relevant and something we should all be looking forward to. So what I've tried to describe through the first two-thirds of this discussion is that there are a lot of things that are changing that are tangential to or fundamental to material parts planning. But we will still have a critical role in the ability to sustain assets in the field over time. And we like to see us specifically having a leadership role in driving that through our generation advanced data science, which we've been working on for decades effectively, and the independent validation of our technology. Our optimization, for example, has been vetted by Logistics Management Institute and Boeing and Lockheed and Capgemini and the U.S. Air Force and a number of people who have very, very challenging uses for this application. We have the most experienced team working on this. I started my 40th year in service parts planning this month. We have a large, thriving, and very challenging client network, which we've been working extensively with the COVID to help them understand the implications of either rapid rise or rapid drop-off in demand and changes in lead time and availability. And we think that drives the greatest value. We partner with some of the best people in service in the world, and we have therefore have some pioneering integration across the platform. And what I'm going to close with is that while the service will still require service parts planning will need to adapt because the sources of data and the uses of that data are going to change. 10 years ago, all we thought about was talking to an ERP, an EAM, a CRM system. Today, we have a much more complex array of products that need to be combined. Now, this is the Servigistics platform, which is an end-to-end, but obviously there are lots of alternatives in the marketplace. We just offer the only one that's already out of the box, fully integrated. But what we're now looking at is the ability to capture data directly from the assets through ThingWorx, apply that to big data and the first utilization of machine learning to understand the implications of the data that's being captured, allow connected SPM to begin to replace that proxy data in forward-looking forecast methodologies that radically changes the demand plan. And then the optimization and the supply planning largely operate as they always have, but the supply plan needs to be mindful of potential impacts of things like 3D printing. And of course, the demand plan will need to understand the impacts of predictive maintenance. And then because we have these huge volumes of data, can apply these performance analytics and intelligence on the top of this to refine the model and begin to look at a path towards automated planning or autonomous planning. And maybe even in situations where we need to validate results, we can look at applying a simulation to be able to look at how different changes that are being suggested might play out in the real world. So I think that may be my time, Bradley. I will hand it back to you.
Thanks a lot, Ed. That was great. Perfect timing as well. We appreciate you taking some time and walking through that with us. I'll just share a couple ideas here. One, we can take the Q&A section to offline, and feel free to send in any emails either to Ed or myself. We're happy to take those questions and provide some response there. But also, we'd like to invite you to participate in the virtual LiveWorx, which is taking place next month, June 9th. Ed and A host of other speakers will be talking about some of these service parts management topics that you see on the screen. And we invite you to participate there by going to LiveWorx.com and getting registered. It's free. It'll be a one-day event. You'll have access to this content, and it'll be, I think, beneficial for all of you. And then also just follow us on the LinkedIn page for future invites to webcasts and other events that we're participating in as those events start to ramp up, hopefully in the fall. With that, Ed, I'll just thank you again for sharing your expertise. Thank everyone for taking the time to join us today and participate in this discussion. We welcome many of those questions via email. And with that, we'll say thank you and have a great day.